Hey everyone, welcome to the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I'll gather them up and I'll answer them here. I record this show every Monday at 5 p.m. Pacific time. So if you want to ask your question directly, live, oversee the answer, post follow-up questions, argue with people in the chat, then come and join on the live show. It's a lot of fun. And it's about double, maybe triple the length of the show that you're watching right now. So come on, Mondays, 5 p.m. And I'll make sure that the next event is around here somewhere so you can click a reminder. And here's the secret pro tip that's the permanent location of the video. So even though we unlist the video, if you bookmark that episode, then you can still see it afterwards. We just hide it because the YouTube algorithm punishes us brutally if we leave too many longish videos on our channel. All right, let's get into the questions. My life in videos. How big would a telescope have to be to see a star in the Andromeda galaxy? Because isn't it true that every exoplanet or star system that we have observed has been in our Milky Way? You could observe stars in the Andromeda galaxy with a backyard telescope, and not a very big one. It's not that difficult. And the reason is because there are a lot of very bright stars in Andromeda, and there are a lot of stars that are actually quite far apart from each other. So yeah, if you had a whole bunch of stars really close together in the core, where they're just a couple of light years apart, then you're going to have a really hard time distinguishing them, and even the Hubble Space Telescope is going to have a hard time. But if you're looking at just sort of mainly through the galaxy and definitely towards the outskirts, then the distance between the stars get larger and larger until they're 10 light years apart, 20 light years apart, 30 light years apart, and they're very easy to distinguish as individual points of light from each other. And in fact, the way we know about the expansion of the universe comes from Edwin Hubble's ability to resolve individual stars in other galaxies. Hubble was focusing on these Cepheid variable stars, these stars that change in brightness over the course of some very set period of time. And he was able to observe individual Cepheid variables in Andromeda and track them and figure out what was their relative speed compared to us, and he used that to help calculate the expansion rate of the universe. But Andromeda is moving towards us, and so that's a really bad way. So he had to go farther. He had to look at galaxies that were tens of light years away from us, tens of billions of light years away from us, and still could resolve individual stars in those galaxies. So yeah, you can resolve individual stars. And one of my favorite pictures is like a huge mosaic taken of Andromeda by, I think it was Hubble or some ground-based observatory. Like, it's enormous. And you can just see all the stars in the galaxy. And that just shows the power of telescopes and also just sort of the power of all the bright stars in Andromeda. Gunter Raphael. My dear friend, to categorically state that the universe is much larger than the observable universe seems to be not only a meaningless statement, but also a false claim. It simply makes no sense at all. Why? Anything that cannot be sensed, measured, or experienced, observed, cannot influence us in any shape or form, and therefore, there is no way of knowing anything about it. But what you say is that it is to be believed that the universe is larger than the observable universe, but there is no certain way of knowing anything about it. The difficulty with that is that evidently there exists no clear and agreed upon workable definition of what space actually is. So this is based on, I guess, a couple of episodes ago, we talked about just sort of like how big is the actual universe compared to the observable universe. And I guess me saying that it was almost certain that the actual universe is bigger than the observable universe rubbed you the wrong way. So let's go into the evidence of how we know that the actual universe is bigger than the observable universe. And the first piece of evidence that I mentioned to you is that astronomers look into the cosmic microwave background radiation, and they look to the left and they look to the right. And they look up and look down and look in every single direction. And what they're looking for is some kind of either repeating pattern, right? Like imagine mirrors in front of you and mirrors behind you. And you see yourself and you see yourself and yourself off into infinity because you're being reflected back and forth. So imagine that in the universe. So if we saw sort of the same structures on opposite sides of the universe, then we would say, okay, when we look in one direction, we're looking back at ourselves from the other direction. But how did astronomers know that the universe is bigger than the observable universe? And the way they do this is try to estimate the shape of the universe. And it's going to sound really weird because I know you're imagining the universe as this great sphere. So again, imagine this universe as something that just goes on infinite in all dimensions, 3 dimensions, or something that wraps, but still in 3 dimensions, like a 3D game of asteroids. So don't think of a sphere. That will break your brain. What astronomers do is they have sort of 2 main lines of evidence. And the first one is to measure the curvature, the shape of the universe through geometry. And you can do this on the Earth. And so now we're back to a sphere, which is going to kind of muddy the waters. But anyway, so imagine you're on a sphere and you draw the biggest possible triangle that you can. You start in the North Pole, you come all the way down to the equator, you go all the way across to halfway along the equator, and then all the way back up to the North Pole. And so you've drawn a triangle. And if you measure the angles on that triangle, you're going to get a measurement that is bigger than 180 degrees. And that is because the triangle is sort of opening up as it's going wrapped around a sphere. But if the sphere was so big, just like impossibly large, then it would still feel like it's 180 degrees. You wouldn't be able to measure the curvature on planet Earth, even though it's there. And so astronomers have gone out and looked for the largest triangles that they can measure in the universe. And this is the features in the cosmic microwave background radiation. They're looking at features that are billions of light years across. And when they do their most careful calculations, what they get is that the triangles in the sky match 180 degrees. So that means that the universe is flat. And we'll talk about what flat means in a second. So the other way that astronomers calculate the flatness, the shape of the universe, is they measure the mass density of the universe. The question being, is the universe got so much mass that it's going to collapse in on itself? Or does it have so much mass that it's going to just get more and more diffuse over time and just expand out into nothingness? Or has it got the right amount of mass to match the size of the universe that it's going to keep on expanding until it just slows down to a halt, but at infinite range? And it's this third answer, that the universe appears to be flat from that perspective as well. And so imagine that you are an ant standing on a sphere, a giant sphere, a sphere the size of the Earth. And from your perspective, the sphere is flat. You're going to walk in any direction. It appears the landscape, you can't see the curvature of the horizon. You're just moving around on this 2-dimensional structure. And so the Earth is going to be bigger than your perception, but the Earth does wrap on itself. It's just bigger than you can perceive. You can just take that idea and scale it up one more time into the universe. When astronomers go out and try to measure the shape of the universe, the flatness of the universe, the curvature of the universe, it is, for their best possible measurements, flat. And so what that means is that the actual universe is not smaller than the observable universe, because the curvature would be very obvious. The universe is not even the size of the observable universe, because again, the curvature would be very obvious. The actual universe has to be significantly larger than the observable universe to achieve either a flat infinite universe that goes on forever, or a universe that is so big that we can't measure the curvature. And so that's why astronomers think, and I think it's like 1,000 billion light years at a minimum. It's like, that's how big it would have to be. Any smaller than that, and we would be able to start detecting the curvature here in the universe. And all attempts to detect that curvature have failed. So astronomers have a lot of great ways to remotely, I mean, that's all astronomers do, is they detect things remotely, and they learn a tremendous amount about the universe. Smoke. Black holes are solid objects, right? A lot of depictions show black holes like actual holes, like a drain. And if you drove a spaceship into a black hole, it would be like hitting something, not like disappearing into some other dimension. Or am I crazy? Yeah, you can definitely ignore the pictures that look like a drain, because that's really only perceiving what a black hole might look like in 2 dimensions. If you were going along a flat table and then suddenly there was this singularity down at the bottom of this long hole, then you would be falling into a two-dimensional black hole, but it's really in three dimensions. Whatever direction you're coming at the black hole in, you are falling into the gravity well. In the same way that any part you are standing on the Earth, you are falling into the Earth's gravity well. The same drawing would work perfectly for how the Earth's gravity well, just not as deep. But what you're asking, what is inside the black hole? And so imagine you've got this event horizon, and that's the point at which you have to be going faster than the speed of light. The escape velocity is faster than the speed of light. And inside that is the black hole itself. The sum accumulation of all the mass and energy that has fallen into the black hole is inside that event horizon. But what actual form does the black hole take? We don't know. One possibility, as you said, is there is an actual solid object just a few meters below the surface of the event horizon, and that's where the black hole actually is. And so the second you fall into the event horizon, you smash onto the top of the black hole and smear out into a paste on the exterior of the black hole. The event horizon expands a little bit and waiting for the next meal. And so the event horizon is always outside the black hole itself. Another possibility is that all the matter in the black hole is compressed down. There's nothing to stop it from just compressing faster and faster. And it just gets down into an infinitesimally small point of infinite density at the center of the black hole. And maybe it's like continuing to accelerate its contraction faster and faster and faster. And we don't know. We don't know what the answer is. And we may never know. There may be no way to actually figure out what is the shape of the thing that is hiding inside the event horizon. But for all practical purposes, for mathematics, from the outside, which is the place we can actually observe it, astronomers sort of assume a point of infinite density inside the event horizon. And that's how they do all their math. Maybe one day we'll be able to figure it out. Dave. Hi, Fraser. If the moon was created by a protoplanet slamming into the Earth, how did the moon make the first orbit without a home and transfer or something like that? We've talked about this a little bit, that you can't get into orbit with one kick. So if Superman tried to punch somebody into orbit, he could punch them into an Earth escape trajectory, or he could punch them into a ballistic trajectory, but not into an orbital trajectory. They're always going to come back down. The only way to remain in orbit is Superman punches you into orbit, and then you fire some kind of propulsion system to circularize your orbit when you reach the top of your orbit. It's the only way to sort of not come back to Earth. So then you're kind of imagining, right? Back billions of years ago, this giant Mars-sized object crashed into the Earth and sprayed it all as debris, and it somehow turned into the moon. Well, why didn't all this stuff just all fall back down? And the answer is that most of it did. But you've got just this enormous debris cloud that has gone up into space and is trailing behind the Earth, and all the pieces of debris are colliding with each other and giving each other energy and taking away energy. And some of them are getting kicked all the way out of the Earth's gravity well. A lot of it is being churned back down into the Earth, but some of it was able to, through its interactions, essentially circularize its orbit. So the pieces of debris stole momentum from each other to circularize the orbit, and then you got this moon forming in orbit around the Earth out of all of this accreted material until it was able to form into a sphere and clear out everything else. And here we are today. Ethan Jacob Broska. Do we ever find pieces from Earth on other planets? Yes, we have found a piece of Earth on the moon. So after the moon had formed, some big asteroid crashed into the Earth, kicked up a chunk of debris, and one of those pieces of debris landed on the moon. And then that debris was smashed by other asteroid strikes on the moon, churned up, mixed in, and eventually most of it was mixed into the moon, but a piece of it was left out, mixed in, like a few grains of the Earth were mixed in with a chunk of rock sitting on the surface of the moon. And then an Apollo astronaut picked it up, put it in a bag, brought it home to Earth, and actually did a video about this. One tiny little piece of one of the moon rocks that the astronauts brought back has a piece of the Earth in it, and it actually tells us a little bit about the formation of the Earth through the moon, which is crazy. But that's it. We haven't found any pieces of the Earth on Mars or on Venus or any other place. It's theoretically possible that there are meteorites from Earth on, say, the surface of Mars, but it would be pretty tricky. Most astronomers assume that the vast majority of the meteorites that we're going to find came from the moon, landed on the Earth and Venus, etc., because Mars has a much smaller gravity well. It's much easier, with a giant impact to send a chunk of rock into a escape velocity from Mars because it's so small compared to trying to get something off of the Earth. So we haven't found any yet. So far, we've found meteorites from Mars, from Vesta, and a couple of other asteroids that we know of, but nothing significant so far. Brenton Rashid. Hey, Fraser and team. Hi, all. So good to be on the live show. Question you'll probably cover anyway, but now that James Webb is in position, how long till the science images? We're looking at about 5 months officially from now till we get to see those first images. So at the time that I'm recording this, James Webb just arrived at its L2 Lagrange point. They've already removed the clamps on all of the mirrors, so the mirrors are able to fully swing, but they're still not aligned as much as they need to be. They need to be, they're millimeters off from each other. And so the vast bulk of what's going to happen now over the next several months is one by one, the Webb team is going to be aligning these mirrors down to tens of nanometer precision. And that's going to be a very laborious process. So that's what we're waiting for now, is for them to fully align all of those mirrors to be able to take their first images. And until then, the images will be blurry and not very useful, but they'll get better and better and better as each mirror is perfectly put into place until the whole primary mirror acts like a single big connected mirror. So stay tuned, still like May, June. So I'll let you know when we get the first pictures. Moonwalker, considering that it took 20 years to build the James Webb Space Telescope, could some of the tech inside be considered obsolete by the time it was launched? I wouldn't say that the technology would be considered obsolete, but obviously if the people involved had the chance, they would swap out a 15-year-old computer and replace it with an absolutely modern computer. But that said, in general, space missions use older technology anyway for reliability and space hardiness. They want to make sure that the gear that they're using has been proven to work in space. And so it takes quite a while for this technology to get used and improved and so on. But also, a lot of the tech that's in James Webb was invented for James Webb. It doesn't exist in any other telescope, ground-based observatory, anything. I'll give you a couple examples, like the sun shield, right? No one has ever built a sun shield like that with all the actuators to move it into this shape. The folding mirror system, nobody's ever done that. Even the actuators I was mentioning, like they have to be able to move those mirror segments on James Webb to within a few dozen nanometers of each other. And that technology didn't exist, so they had to invent it for James Webb. So I think what you would find is that, sure, there would be some parts, some controllers, some CCDs, some instruments that they would love to be able to have the modern version that's a decade newer, but so much of the telescope was just invented, developed, custom for this one job and doesn't exist anywhere else. More questions in a second, but first I'd like to thank our patrons, Jeffrey Kajowski, Avram Rosen, Bill Kraus, Brenton Rashid, James K., and the rest of our 808 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universetoday. Dark Jedi Order. Is it possible that dark matter is actually just black holes? One of the ideas for dark matter is primordial mass black holes. They would perfectly explain dark matter. In the very beginning of the universe, you would have these ripples, these sort of overdense regions in the universe that were so dense that they would just turn into black holes naturally. And if you do the math, as long as the black holes were between like the mass of the moon and 1,000 times the mass of the sun, then they would work out as dark matter. But astronomers are trying to constrain this. They're doing enormous surveys where they're looking at galaxies and watching to see black holes shifting inside those galaxies. They're causing gravitational lenses to distort the light as they pass, say, in front of a star. And they'll be able to then say, okay, if dark matter is primordial black holes, then they have to be 100 times the mass of the sun, or they have to be the mass of Jupiter. Like, they'll constrain those limits, and eventually they'll either discover them or constrain them away so that there's no possible way that primordial black holes are dark matter. I mean, the most likely answer to like what is dark matter is that it's probably just a whole bunch of things. Like, some portion of it could very well be black holes. Some portion of it could be sterile neutrinos. Some portion of it could be axions, some other kind of particle. And as you discover these parts one after the other, the total adds up to account for all the dark matter in the universe. But so far we haven't found any of them. Mazahir Mamadi. Hey Fraser, how come James Webb orbits around a blank point in L2? Well, L2 is one of the Lagrange points. And the thing that's great about L2 is that it is gravitationally stable. You don't need a lot of propellant to loiter around in that area. But why even go to L2? Why not orbit around the Earth? And the reason is because James Webb needs to keep its mirror incredibly cold, just a few degrees above absolute zero. And the way that it's going to do that is it's going to block the hottest three objects in the sky: the sun, the Earth, and the moon. And so the cool thing about being out at Lagrange 2 is that it can take the sun shield, put it up, block the Earth, the sun, and the moon all in the same area. And they will always be blocked because they're all close together from the perspective of L2. And then the mirror in the shadow of the sunshade will now be able to observe the universe. And then as James Webb follows the Earth as it goes around the sun, it will see a different part of the sky every month. And so once a year, it will be able to see the entire sky. It's really ingenious on how this whole mission is going to work. L2 is great for this kind of thing. John Gannay. If we could look at the sky of the primordial Earth 4.5 billion years ago, would there be an appreciable difference between the sky of a universe a third younger? That's an interesting question. So what is different about the earlier universe? 4.5 billion years ago is not that much. The vast amount of star formation that happened in the universe really happened in the first, say, 5 billion years. So you wouldn't see galaxies awash in star formation the way you would at the early universe. And so you would have to kind of go back to the first few billion years to see something quite dramatically different. Galaxies would be a little bigger and a little closer than they are, but the universe wouldn't look that different from your perspective 5 billion years ago, 10 billion years ago. It really wouldn't look that different. T260. Hey Fraser, what is the next launch that you would like to see in person? New Glenn, SLS, Starship, perhaps all three? The only rocket that I watched was OSIRIS-REx, which launched on an Atlas rocket, and it was cool, but it was a fairly standard launch. Doesn't hold a candle to these big rockets that are coming. And all of them, Starship, SLS, New Glenn, are going to be monsters. And I think there's something really cool, the sort of the visceral feel. Like, one of the things that's amazing, when you watch a rocket launch, and we were standing on the water, like beside one of the inlets at Cape Canaveral, and the rocket takes off, and the shock wave of the rocket exhaust, the sound coming off this rocket, cross this bay, and you feel it, like it's sort of hitting you, and you can feel it in your chest. And it would be so much more if it was a bigger rocket. So I would love to see like Starship take off with super heavy. And then you could watch as the booster returns back and lands, gets caught by Mechazilla and then put down gently. And then maybe later on a Starship lands and gets stacked up again. Like, there'd be so much cool stuff that you could see while this whole process is happening rapidly. So I think of those, I would love to see Starship because it's so weird and so different compared to SLS. SLS would just be like a really big rocket taking off. You'd feel it. It'd be bright. You'd hear it, but then it would be gone over the horizon. Same thing with New Glenn, because its booster would be landing out on a ship in the ocean. But Starship is the one where a lot of really weird, intricate things are all going to happen all at the same time. So I think that would be the one that I would love to watch in person. And if their launch cadence goes up to the point that Elon Musk is hoping, then it should be relatively easy to do. They'll be launching every couple of days. So that'll be the one. D3D3. What is the next big project besides the Webb telescope? Yeah, it's funny. It's like all of our focus and energy has been on James Webb. It's all we've been worrying about, all we've been excited for. And now James Webb is gone. It's at L2. It's getting aligned. And so now we're going to have to wait several months before we can see that first picture. So, like, what's the next big project? Well, we've got the first launch of the Space Launch System coming up in March. We've got the launch of the SpaceX Starship in the next couple of months. In theory, we're going to have the launch of Blue Origin's New Glenn. We've got the Vera Rubin Observatory coming online in later 2022. And this is like the telescope I'm the most excited about. Then, sort of when you think about longer term, we've got the development of the Europa Clipper and launch in just a couple of years. We've got the Titan Dragonfly, which is going to be sending a nuclear-powered helicopter to Titan. We've got the Aerial Space Telescope, which is going to be observing the atmospheres of thousands of exoplanets. We've got the European Extremely Large Telescope coming online in 2026. We've got the Giant Magellan Telescope, which is a 30-meter class telescope. So there's a ton of really exciting mega astronomy spaceflight projects coming. So this should keep you entertained while you wait for that first image from James Webb. Garrett Schultz, will Vera Rubin be able to see James Webb? People keep asking me, like, will anybody be able to see James Webb? You can see James Webb with a fairly powerful backyard telescope. You definitely could see it as it was leaving and making its way out to the Lagrange point. Hubble could see it. A lot of telescopes on Earth could see it. Vera Rubin will definitely be able to see it. But nothing will be able to observe anything but a dot. So from a really powerful backyard telescope, you'd get a dot. And from the Hubble Space Telescope, you would get a dot. And you'll never get anything in between. It's kind of like the same thing with observing a star. Like, you can observe a star with your backyard telescope and you see a single pixel, a single point of light. And the Hubble Space Telescope observes the same star and sees a single point of light. It's just that Hubble is seeing it more brighter and is able to break up the star light into the various chemicals that make up the star. But at the end of the day, you wouldn't be able to resolve anything more than a point. Robin McCullers, what in your opinion do we live in as in this universe? Are we in a black hole or a simulation? What are your thoughts? I don't really have an opinion. We don't have enough data to make a decision either way. And if you don't have enough data to make a decision, then you kind of just have to assume that the universe that we live in is as it appears until more data comes. And there's a lot of evidence that everything is sort of predetermined. There's no such thing as free will, and yet you just have to act like there is free will. The simulation hypothesis is interesting. It's hard to argue against it, and yet there's no evidence for it. And so you just have to assume, you have to act as if you just live in a regular universe. So no, I don't hold an opinion. I live this life as if I'm made of meat and will die, and no one will go anywhere else. And so every day that I waste here on Earth is a day that I'll never get back. So that's why I try to sort of live life to the fullest. So anyway, yeah, I don't have an opinion. Verstuffsec. What if some micro-meteorite impacts James Webb on its way to L2 and ruptures its thin sun shield? Is it possible that happens, or I'm just paranoid? It's almost inevitable that micro-meteorites are going to impact the sun shield of James Webb. And they're going to punch a teeny tiny little hole through the sun shield, and it's going to make essentially no difference. And that's sort of one of the reasons why James Webb has this multi-layered sun shield. Because if you've got a puncture that goes all the way through all of the different layers, then any sunlight is going to come through. It's going to fall as like a shadow, and it's not going to make it all the way back to the telescope. But nothing is going to, it's not like the sun shield is like perfectly taut and all it needs is just one little piece to tear it open, and then boom, it's exposed to sunlight. These little micrometeorites can go right through the sun shield, burrow a teeny tiny little hole, and go right through. So don't worry about it. NASA thought of this. And they're expecting it to happen. It's almost guaranteed that this will happen. Could it be hit by something bigger? For sure. But the chances of that are incredibly low. So don't worry about it. Scott's Astrophotos. What are some future tech ideas to incorporate into a future space-based telescope? So there's a couple of ideas that I've been following, and I did a video about this a couple of years ago about like what are the telescopes that come after LUVOIR. And a lot of the ideas, they come into fairly similar themes. So the first idea is this idea of interferometry, where you add the light from multiple telescopes, which are separated apart. And if you get them perfectly aligned into the wavelength of the light, then they act as if a single telescope that is the width of the gap in between them. So you could put one Hubble Space Telescope over here and then put another Hubble Space Telescope a kilometer away from each other, align them perfectly to within a few hundred nanometers of each other in space, which is possible. Then they act as if a telescope that is a kilometer across in terms of their resolution. And that would allow you to resolve features as if you had a telescope a kilometer across. But the downside is it doesn't make things brighter. So if something is fairly dim, you can't resolve it because you can't see it. And so the trick to resolve something that's very dim, the idea that I really like is this idea of sending up dumb telescopes. So instead of a really precision, large mirror telescope, you could send up a bunch of telescopes that are, say, 5 meters across, and they're fairly crudely built. And they can fly in formation, and they don't even have to fly perfectly. And they can act like a single telescope. Now, you don't get the interferometry, you don't get the baseline of their separation, but if you have two telescopes that give you, say, 25 square meters of surface area, then if you add the light of both of them, you get 50 meters of surface area. And if you launch another one, now you've got 75 meters of surface area. And if you launch 50 of them, you can sort of see where this is going. And it's this idea that you don't get all those cool advantages of interferometry, of the bigger baseline, but more mirrors in space all pointed at the same thing gives you more photons and gives you a better picture. And so there's these ideas to just launch these flotillas of space telescopes that can act, you point them all at the same object and they act as if they are a bigger telescope purely by the size of their mirrors. It's just additive. And so if you want more telescope, you just launch more of these telescopes, launch another 5, another 10, and they just fly in this flotilla and it just gets bigger and bigger over time. And then the last idea that I really like is the idea of just space-based construction. So with James Webb, they had, a lot of the cost and expense was to fold up James Webb and make all of its electronics fit within the Ariane launch fairing. But what if you didn't have to worry about that? What if you launched the telescope pieces at a time and then constructed them in orbit? And that's what was done with the International Space Station. You can imagine something similar where you've got this core bus of a space telescope and it's got robotic arms, preferably built here in Canada, and you launch the solar panels, and it grabs the solar panels and bolts them onto the side of the telescope, and you send the primary mirror, and it grabs the primary mirror and attaches it to the top of the telescope, and so on and so forth, until you've built out this telescope that is far larger than anything we could launch in one single launch. And I really like that idea. So my guess is future telescopes are going to incorporate those three ideas moving forward. Forza Jersey. Will we have a permanent human presence on the moon by 2050? I mean, we don't know what the future holds, but my guess is yes. That I would guess that by the late 2020s, we will have a permanent base of some form on the moon. So we don't have to wait by 2050. We will have some research station on the moon by the end of this decade. Maybe the astronauts are going to arrive by 2026. They're going to leave some sort of station down on the moon within the next couple of launches. And by late 2020s, early 2030s, you will just see astronauts going to the moon, down to the surface, going into the station, and swapping back and forth. And I think that's the extent of the human presence that we'll see on the moon, is a handful of astronauts in a ever-growing space station on the moon. Mark Elkin, is there any evidence of extrasolar Oort clouds and or Kuiper belts? Not extrasolar Oort clouds. We haven't been able to observe our own Oort cloud. The only evidence we have for the Oort cloud is that we have these long period comets that fall down into the inner solar system. And I guess the fact that we're seeing interstellar comets like Borisov would be some kind of indication that there are interstellar Oort clouds, but we haven't been able to detect any directly. Now, Kuiper belts have been detected. So astronomers have detected a ring of icy material surrounding a planet. Maybe a couple of times, but I know once for sure at a great distance from the star. So, they're denser in the Kuiper belt. The objects are denser, are more easy to observe. So that is definitely something that is possible for us to observe now and in the future. All right. Well, those are all the questions that we got this week. Thank you, everyone, for submitting them. Thanks for everyone who watched the live show and asked your questions and follow-on questions and stuck around for overtime. It was super fun. And remember, we do this every Monday at 5 p.m. Pacific time. So we'll see you all next week. If you want a single comprehensive resource for space news, you'll want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights, and links so you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all my videos are also available in a handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes. Thanks to all the moderators, and a special thanks, as always, to Chad Weber and Nancy Graziano.